Hello everyone. I believe this will be your final lesson or lecture for the topic on heterocyclic chemistry. So I will be taking all of you through the final lesson. It will be around 20 to 30 minutes where I'll be introducing you to something a little bit different from what you have learned so far, because I do believe that thus far, you have learned heterocycles such as thiophene, furan, pyridine, pyrrole, etc. So today I'm going to just show you something a little bit different. So a little bit about myself. You can check out my profile from the La Trobe webpage. I'm actually a honorary visiting fellow. But I'm not based in Australia. Actually, I'm based in Singapore. So yeah, so I'm actually helping Dr. Hong to actually do this final bits, and also to give you a little bit of a snapshot on some of the interesting literature showcasing the application using heterocycles. Okay, so without further ado, I'll just dive straight in. Yeah, so what I'm going to focus on will actually be on a topic known as molecular machines, which actually received the Nobel Prize in 2016. Okay, so it's actually awarded to Jean-Pierre Sauvage, Sir Fraser Stoddart, and Bernard Ferengal. Okay, so for their development of the world's smallest machine. So this is what we call molecular machines. If you are interested, there are some materials for you to download, which I have already sent to Dr. Hong, so you can just take a look at them. Yep, so this is how they look like. So they jointly received the Nobel Prize 2016 for their work on molecular machines. Yep, so I will just focus on bits and pieces of their work so that you can get a glimpse of what exactly molecular machines is. It's actually a very huge topic, so huge that I think it could probably take one whole module, maybe a 30 to 40 hours module, simply talking about molecular machines, which I'm not gonna do that, because that's not the purpose of the talk today. Yeah. Okay, so what I'm going to focus on is just to introduce you to two interesting papers, either two or three, depending on the time. Okay, if it's three, then I'll just go a little bit fast. Just show you a little bit about what these work are about, so as to appreciate, so that you can appreciate what you have learned so far. Okay, so the first piece of work I'm going to showcase to you is actually done by Professor Ben Ferengo. So this gentleman on the right, yeah, he's actually one of the Nobel laureates, okay, who received the prize in 2016. Yeah, so I'm just going to go straight into what he actually did. So if you look at the title of this piece of work, it's actually called Reversible Unidirectional Molecular Rotary Motor Driven by Chemical Energy. Okay, so basically, if you look at it, so it's actually a structure. It's a chemical structure where if you subject the structure to some form of chemical reaction, it will just rotate from, say, at the beginning we are at station A, so you rotate from station A to B to C to D and then back to A. Okay, so from a chemical structure perspective, maybe I can just show you this particular diagram. Okay, yeah. So we start off from this particular structure 1A. You can see that it's lactone. I hope that's something familiar. So maybe I can just highlight. So this particular portion is known as a lactone. Okay, because or otherwise we call it a cyclic ester. Yep, so it's a fused ring, so there are 4 fused rings together. Yep, so what happened is that over at this end, right, there is a protecting group protecting one of the phenolic OH. Okay, so just for you to take note of it, so it protects one of the phenolic OH. Okay, so in the first reaction, you'll notice that they actually used this particular reagent, which is the S isomer. So I do believe you know what all these stands for. So R and S, so it's one of the enantiomer. 2-methyl CBS. So this is a reducing agent. Okay, so this particular reducing agent actually perform a stereo selective reduction, okay, to give you a diol. Okay, so in this case, of course, this is actually the phenolic OH and this is the alcohol. Okay, you'll notice that you are only getting one of the products. So meaning, how should I put it? Okay, so let's say if I put my eyes over here, okay, I look at it from the top faced, okay, so I'm actually just getting this particular product. OH is here, and then OB MP or PMBO, whatever, and then after that you get the other one like this. Okay, so so that will be the one with the OH here. Okay, so you are getting this. Okay, instead of the other isomer where it will look like this. Okay, so the other isomers will look like this. So instead of the OH here, now the OH is at this direction, and then OPNB, and then OH. Yeah, so you're actually getting one this particular we call it heteromer, but you don't need to know that term for now, okay, because the kind of stereoisomerism, I'm not sure whether it's written somewhere. If you are interested, you can read about it. I vaguely remember seeing the term, okay, but it's it's a special kind of stereo isomerism where the restriction in ring rotation prevents the structure from interconverting from one isomer to the next. Okay, so just for your information, so we call it heteroisomers. Okay, so yeah, so we're only getting this. So I'm sure you can tell that if I'm using the R isomer, I will probably be getting this. Okay, so that's what we meant when we say stereo selective reduction. Okay, so yeah, so this is a bit difficult to look at, so that's why I draw a structure, something I mean so for you to visualize. Okay, and then after that you actually subject the subject a based carbonates and then a allyl bromide. So it's some form of SN2, so a nucleophilic substitution. So this particular nucleophilic substitution, why do we do that? There are a few reasons. I think number one, the reason is to remove the acidity and of course to prevent any potential reaction. And of course, the second thing you might realize is that actually in terms of steric demand, the two OHs are actually not very sterically hindered. So in that case, it is actually possible for this structure to actually rotate back to give you this. So in order to prevent the rotation, I need to block one of the face, or rather, I need to block one of the structure. I need to incorporate some form of steric demand. So in this case, I'm incorporating a steric demand in this to convert into O allyl, and then I perform an oxidation as well, just to make it look a bit bigger, and then to give you a carboxylic acid, and then you realize that the rotation is kind of clockwise like this. Okay, so now we get 1B, and then after that, interestingly, I remove the protecting group, and then it rotates one more round. But before we allow it to rotate, what we do is we remove the protecting group to change it to OH. Okay, and then you realize that when we change it to OH, it's no longer so sterically hindered, so it can then complete the other rotation. So you will now rotate around 180, about 120 degrees maybe, so that this OH eventually will then form form a lactone or a cyclic ester. Okay, yeah, and then after that, what they do is they are going to perform the same thing. So if you look at 3I over here, that's reaction 3. Yeah, so they are using the same reducing agents, okay, S2-methyl CBS, okay, and then very specifically, I'm getting this particular heteroisomer, Okay, and then I'm going to do the same thing. I'm going to protect the phenolic OH, perform an oxidation, okay, over here. And then after that, what I'm going to do is I'm going to remove this O allow, so to make it less directly hindered, and then the rotation will happen again, and then this completes one cycle. Okay, so that is what they meant when they say that this piece of work is actually a reversible unidirectional molecular rotatory motor, because it rotates one round 360 degrees, um, and it is solely driven by chemical energy. So meaning that I incorporate or I allow chemical reaction to take place, and then the system will simply rotate. Okay, so I encourage you to read this particular piece of work. It's actually a very brilliant piece of work by Professor Ferengo. Very, very beautiful chemistry. Yeah, so I think please go through this piece of work. I know it's not exactly related to heterocycles, because for heterocycles, it did not have the usual furan, perol, pyridine insight. Okay, but usually heterocycles are involved in molecular machines. But I'm going to show you another example next. Then you understand what I'm trying to say. Okay, so yeah, and yeah, feel free to read through this whole piece of work. I think what I mentioned earlier on is written over here. Um, yeah, so you can see that this is a chiral reducing agent. So if I'm going to use RCBS, okay, this whole rotation will go anti-clockwise instead of clockwise. Okay, so that's the beauty of introducing a stereoselective reducing agent. Okay. Yeah, so please go through this piece of work. I cannot guarantee whether you come out for exams. I think you have to ask Dr. Hong, but I think it's a beautiful piece of work which you can understand quite a bit about the application. Because I think so. I think thus far for heterocycles, the things you have learned are largely quite theoretical, and also probably more related to drugs rather. I mean, I'm not sure what you have learned, but I'm just guessing. Yeah, it may be the more theoretical aspect. Yeah, but I think in this case, I think molecular machines show you another perspective. Okay. Yep, and then yeah, if you read through the piece of work, yeah, so they're actually using chiral HPLC to determine the difference between the isomers. So over here you can read that if you are using a chiral sodium boron hydride instead of this, you get actually two peaks with the same intensity. I think it's easy to understand why. Okay, yeah. So yeah, so this is molecular motto. Just one small piece of work, but of course it's a very important piece of work. I mean, if not, it wouldn't be published in Nature, or rather in Science. So this is actually a science paper. Yeah, so it's a brilliant piece of work. So I hope that it will pique your interest a little bit on molecular machines. And as I've said, if you are really interested in the work by the three gentlemen, please go and watch their Nobel lectures. Okay, it's actually on YouTube. Just go and Google their name. I'm sure it will be out. It's actually under the YouTube channel on the Nobel Committee or Nobel Organization, something along those lines. Okay, so the next thing I'm going to show you is on this particular aspect is called pick up, transport, release of a molecular cargo using a small molecule. So this is published in Nature Chemistry, not done by the Nobel laureate, but it doesn't matter because ever since they developed molecular machines, many researchers actually come in and enter the research arena on molecular machines. And then some of you might be wondering why the Nobel Prize is only awarded to three of them. So basically, the Nobel Prize is awarded to people or to scientists who are the forefather in developing the field. So they are usually the first who comes into the field in question, and then they make it so popular, so powerful that people begin to enter the field in order to develop something more interesting. Okay, so another example would be the Nobel Prize in 2021 this year. It's actually given to Professor Macmillan and Professor Benjamin List for their work on organocatalysis. So they started their work in the late 90s. They had their groundbreaking paper in 2000, and people realized that this is actually an amazing field to go into. Yeah, so after they made some good progress, so many people actually entered the field. Yeah, so that's the impact of powerful research. So powerful research is where you develop something interesting and significant, and people will follow suit. Yeah, and Nobel Prize, well, I mean, it's usually given to the first few who actually discovered or uncovered the process. Okay, I'm not going to go into too much detail because over here the molecules is really huge. Okay, but basically what exactly is happening here is that I'm just going to use the cartoon to briefly illustrate to you what is the thought process of this whole piece of work lah. Okay, so what you have is you have something like a lever here, and then after that it turn around and then it attached to this cargo, and then after that there's a detachment here, and then it turns around and then it releases it into the green box, and then it detaches itself. Yeah, so as simple as that. So essentially you're moving the red sphere, okay, from the left to the right. Okay, it's very easy in everyday life, right? I'm sure you have seen this in everyday life, in supply chain, or in the industry making cars. Yeah, but at a molecular level, I think this is probably the first piece of work being done. Okay, so what exactly is happening at a molecular level is that, okay, I think the first thing is they try to synthesize the system first. Okay, so I think the color code it exactly mirrors what you have above. Okay, yeah, so essentially they want to bring the red parts to the green parts. Okay, so let's see if it's successful. Of course, in real life, at a molecular level, it involves some form of chemical reaction. It's not like just attached and detached. Okay, it's not that simple. Yeah, so that's something which you might want to find out a little bit more, especially if let's say your exposure to chemical reaction is quite limited. So sometimes you might not be very familiar on what exactly is the process taking place. So it does help if you can read up a little bit more on the various kind of reaction taking place in such systems. So usually they are addition elimination based. Okay, yeah, so I think this portion shows you the NMR studies to tell you that from one end to the other end, actually things changes and how they actually track the production of the product by looking at the relevant peaks. Okay, yeah, so I'm just going to jump straight into here. Okay, so yeah, so you can see that over here, so going from left to right. Okay, so what you have here is that this particular, okay, so this is stabilized by intramolecular hydrogen bonding. Okay, so something happened. Of course, it's described in the paper. You can also read the paper, which will be uploaded. And then this so it switches to the other side, and then now it grabs this whole system via some form of chemical reaction. So this is likely to be some form of oxidation, because you form a disulfide bridge, and then after that the bridge is broken, and then you or rather there's a rotation that takes place, and then this bond is broken, and then you switch over to the other side, and then a chemical reaction takes place between the aldehydes, okay, and the N at the end, okay, the hydrazone like and nitrogen. Okay, then after that a reduction takes place and the bridge is broken, and then you get this, and then after that this thing rotates back to this. Yeah, okay, and then of course this is probably the first example which showcase a part of a system, what we call a cargo, is being shifted from one end to the other end. Okay, yeah, so you'll be wondering what are the heterocycles involved. So the heterocycles involved over here is actually pyridine, and then of course you have quinoline. Okay, so I hope these names are familiar to you. I mean, after attending some of these lessons. Yeah, so the purpose of showcasing you these three papers, I'm going to show you the final paper next, is really to impress upon you that heterocycles, many works has been done, and a lot of things are beyond medicinal chemistry or even materials chemistry. Okay, I think a lot of work that you have been exposed to from the previous lecturers, they are largely related to medicinal chemistry or materials chemistry. Yeah, so I just want to showcase another aspect known as molecular machines. Yeah, so it's largely for exposure purposes. Okay, so the final one I'm going to show you, which has really a lot of application, it's by this young gentleman, Professor Abrahamian. It's actually on molecular switches. So he actually wrote a review paper on hydrazone switches. Yeah, so you also get to read this particular paper. Okay, so what happened is that he started off by I mean, this is probably a relatively interesting paper, which I thought you could start to read this first before you go into the other two lah. The reason why I wanted to show you the earlier two pieces of work, which seems to be a little bit more hardcore, right, is that I think in terms of impact to the community, or in terms of achieving the first, I think they achieved the first in this case a full rotation, and then in this case getting a, a moving a cargo from one end to the other end. Yeah, but of course not to say Professor Abrahamian didn't achieve any first lah, but um, his work is a little bit simpler because it's on molecular switches, but it's also amazing because he's able to take inspiration from some of the work done by earlier forefathers, and to bring in and maybe make it look even much better. Okay, and he's able to incorporate a lot of his ideas. So it will be wonderful if you can read this particular chemical communication research paper. Yeah, he studied under Professor Stoddart. I think it's written over. He did his postdoc with Sir Fraser Stoddart. Yeah, so yeah, so you might be interested, you know, like to know that actually the community is quite small, so most of them are linked to one way, in one way or another. Okay, so I'm just going to go straight in. So what exactly is molecular switches? You realize that the transportation, that the cargo system I introduced to you earlier on is also sort of like a switch, because it goes from one and it rotates one round, and then to bring the cargo across to the other end. Okay, so this is just a simple introduction. Yeah, so what exactly happened is that if I introduce UV light, okay, all the pi electron will be promoted, and then your CN bond will have a partial single bond character, and then free bond rotation can take place, and then you'll be stuck here due to hydrogen bonding, okay, between the carbonyl oxygen and the H bonded to the hydrazone group. Okay, besides being activated by electromagnetic waves, we can also change the pH condition to activate the switch. Okay, so we have good examples here, which was being done by the author. Okay, so what happened here is that you notice that this is the preferred configuration of structure 1, because of the fact that the pyridynyl nitrogen, the lone pair over at the sp2 hybrid orbital, is able to form hydrogen bond with the protonic hydrogen of the hydrazone. But once I introduced PFA, which is a strong acid, in, the strong acid will actually protonate the pyridynyl nitrogen, as seen here. So once it's protonated, right, you notice that there will be a switched over. So this whole thing will rotate one round 180 degrees, and then the carbonyl oxygen will then be the preferred hydrogen bonding site to interact with the protonic hydrogen of the hydrazone. Okay, and then after that I introduce triethylamine to deprotonate, and then after a long time, maybe I'm not sure how long, need to check the supporting information. After some time, I think I need to check. Okay, it's not really written, but after some time it will return back to structure 1. Okay, so of course the author also studied the mechanism. on the whole process. Okay, so I think the mechanism is shown over here. Yeah. So this mechanism actually involves some form of tautomerization. If you are interested in the research papers on how they actually studied the mechanism, you can actually download it, um, or you can just check out the from your school website. Okay, so I think it should be available. Yeah. So the whole process actually involved tautomerization, so that this nitrate CN bond has a partial single bond character, which allow bond rotation to take place. Okay, and then when bond rotation takes place, after that, you form the other isomers. Okay, yeah, and of course he did many studies, including replacing the R group with a different functional group, but he realized that actually replacing the R group with carboxylic acid is able to give you this doubly hydrogen bonds, and is able to give rise to some interesting property. So it's able to form something they call emissive hydrogel. Yeah. Okay. So you can actually switch between the two. So in acidic condition, you get this, and then the various degree of pi stacking actually give you an emissive hydrogel. But under basic condition, once you deprotonate the protonic hydrogen, you are getting something like this, and then it loses its emission behavior. Okay, yeah. So Professor Abraham actually talked a lot about this. You can read about it, and then you realize that most of his research has got to do with hydrazone switch. At least that's for the past couple of years lah. I'm sure he has other areas of research. Okay, he also used quinoline, okay, as a stator and for metal coordination. And then this is another brilliant piece of work, because he noticed a very striking problem of using normal acid, because it will actually give rise to the production of salt. Yeah. So what they did is they need to actually do something to address this particular issue. Okay, so they actually use the acid over here. They make use of this phenolic OH acidity. Okay, so once they subject the system to this electromagnetic wave of this particular wavelength, it switch from the trans to the cis isomer, and when the switch happens, there's an intramolecular addition reaction, okay, to form this cyclic ether. And when this cyclic ether was being formed, the H plus being released is being used to protonate the pyridynyl nitrogen, and then allow it to switch configuration. Yeah, so that's the brilliant aspect of this particular experiment. And it can go through over 100 cycles, as opposed to the earlier one, which he did usually around 6 cycles, if not then around 20 cycles. Okay, so in this case we can go for 100 cycles. Okay, so the accumulation of salt is actually an important problem here. So that's something which they need to overcome. Okay, yeah, and of course he described the 4 states of switching to hydrazone 9. Okay, so once you switch to quinoline, you realize that the hydrogen bonds, there are 2 hydrogen bonds being formed to the protonic hydrogen on the hydrazones. Okay, so I need to perform a series of protonation in order to get rid of it. So the first protonation protonates the pyridynyl nitrogen, and then this structure can rotate. Okay, then after that, the next equivalent of TFA will protonate this pyridynyl nitrogen, and then this thing will rotate again. Yeah, and then yeah, so after that, if I introduce a base to it, yeah, then it can then rotate back, okay, to give me the other configuration which is needed. Yeah. Okay, so these are some of the interesting work being done, and yeah, you can read through. Coordination chemistry is also one important aspect. If you are familiar with coordination chemistry, yeah. So if I'm going to use this bipyridine over here, right? Yeah, so if I'm able to introduce zinc 2 plus, where it's a very strong Lewis acid, you realize that the reaction is much faster. Okay, and then you allow this system to actually rotate quickly, because it's able to remove the needs for the protonic hydrogens. Okay, yeah, so I think that's about it. I'm just looking through whether there's anything interesting. Yeah, so basically the back is all on coordination chemistry, and then there is light activated switches, which you can also read about them. Okay, so I hope these you'll find this very short introduction to molecular machines interesting. Um, I'm probably not that interesting, but I just hope that I'm able to showcase to you an interesting aspect of chemistry. Okay, so of course, once again, Nobel Prize given for molecular machines, and over here I showcase to you three important pieces of work. Okay, one on molecular rotatory motor, the other one on this particular transport chain where it's able to pick up and then release a small molecular cargo from one end to the other end using a so-called robotic arm. You realize the robotic arm is also some form of a switch, okay, and then of course introducing you to a hydrazone switch. Okay, yeah. So if I'm not wrong, you sorry, in the next few weeks you're gonna have your tutorial. So I hope you enjoy your tutorials, and then I think Dr. Hong will tell you about your what does your final entails. But do expect related questions on molecular machines to be incorporated in your exams as well, because that is one aspect of application of heterocycles. Okay, so I thank you very much for listening, and if you are interested in fundamental areas of chemistry, do feel free to approach me, or you can email me. You can get my contacts from Dr. Hong, or you can just uh, look at my webpage, okay, and drop me an email, or you can ask Dr. Hong directly. All right.